This presentation will go over field sampling protocols for soil bulk density using the NRCS soil core ring method. My name is Stacy Schwartz, and I will be going through this presentation with you. Let's start by identifying what bulk density is and discussing why it's important. Bulk density for a given soil sample is the dry weight of soil divided by the volume that soil sample takes up. So if you could think about holding a soil sample in your hand that's completely undisturbed, the bulk density of that sample would be the dry weight of soil divided by the volume of your hand that soil takes up. But as you could imagine, determining what the volume that the soil is taking up in your hand would be rather difficult. So as you will see in this procedure, we will use something that is very easy to determine the volume of. Bulk density is an important measure of soil compaction and pore space in the soil. It is also a key indicator of soil health. If we think of these brown circles as different particles in the soil or aggregates, the space that lies between them is called pore space. And in these pore spaces, important things happen. Water and water-soluble nutrients are made available to plants, and also plant roots and microbial life move through and push around through these pore spaces. And so bulk density is very important also for plant processes. The higher the value of bulk density, or the dry weight per given volume, the less pore space is available for things such as root growth, water infiltration, and even seed germination. This table overviews the major soil texture classes and their ranges for ideal bulk density for plant growth, as well as the range of bulk density that limits plant growth. If you want more information on more detailed soil textures, this resource will give you a larger table including a more diverse array of soil textures. There are contexts for which this method for soil bulk density sampling are appropriate, and there are some for which it is not. This method is appropriate for soils that are at or above field capacity, meaning there is enough soil moisture for plants to access the water for their metabolic and regulatory requirements. It's also appropriate for soils with low shrink swell potential. It is not appropriate for soils with high shrink swell potential in which the soil structure is too variable. It is also not appropriate for soils with poor structure or loose soil material. This is because we're using a soil core that is open on both ends, so it's actually a ring. If the soil structure is too poor or the material too loose, you'll simply lose the sample out of either of the ends. It's also not appropriate for deeply cracked or desiccated soils, and it's not appropriate for subaqueous soils. Instead, you can use a vibrocore or other appropriate coring device. Lastly, it is not appropriate for gravelly or rocky soils. Instead, you could use the NRCS Soil Quality Test Kit protocol starting on page 11. There are a few potential interferences with this method. The first is compaction of the sample during the coring process. You know this is happening if the soil elevation inside the core does not match the original soil surface outside of the coring cylinder. If this happens, there has been compaction of the sample and you can no longer use it. Rocks or other large fragments also impede the driving of the ring into the soil. And lastly, cracks on the soil surface also interfere with accurate data collection. There are ways that you can adjust for soil cracking with some math. Okay, let's jump into the protocol. First, you want to gather your materials. This includes a hand trowel, your steel core ring with container, a knife with at least one flat edge, a rubber mallet, a wooden block, and a field scale. You may need clippers or scissors to cut any root material or other plant material extending beyond your soil sample. You also may need additional soil sample containers or even simply Ziploc bags with which to transport your materials if you don't have enough rings and containers for the number of samples you're taking. If you haven't determined the volume of your steel ring already, you can use a tape measure to do so, which is one of our next steps. You'll want to record the weight and volume of the empty core ring and the sample container. The volume for a cylinder is the same as the volume for your ring, which is pi times the radius of the ring squared times the height. Next, you want to make a flat sampling surface. If you're sampling the surface of the soil, this is just the removal of organic matter and debris from the soil surface. But bulk density samples are also taken throughout the soil horizon. So if you're taking it for a specific horizon of the soil, you will have to dig down to that horizon or that area of the soil that you are sampling and then create a flat surface with which to sample on. Then place the core ring flat on the surface of the soil you would like to sample. And then press or drive carefully with a rubber mallet the core ring into the soil. And this is very important to do slowly and with the appropriate amount of force so that you do not cause compaction of the soil sample inside of the core. And this is what it will look like after you've finished driving it in to the soil. You'll see here in this image that there isn't variability in elevation of the soil from outside the ring to inside the ring. So here we do not have compaction. Then you will want to excavate the soil beside the core ring until the whole ring is well exposed, at least on one side. And you'll want to expose also a few inches below the core ring as well. Next, you want to remove the soil sample in the core ring with an excess of soil from below the core ring. This will ensure that we have captured the entire sample inside of the core ring, and we can remove the excess more carefully, making sure that we have an intact sample. Now you finally get to remove the core with the sample. Trim the excess soil and debris so that it's flush with the core. I oftentimes bring it directly into the container, but I wanted to show you guys that there's this soil that's also sticking on the outside of the cylinder that needs removed as well so that it's not included in the sample. But oftentimes, depending on the soil texture, I will take a first cut at the excess debris and soil with the serrated side of a knife, but that final trimming up and straightening up should be done with the flat side of the knife. And then this is what it looks like potentially after that flat edge has gone by. You want to still take your scissors or your clippers and clip off any of the plant debris that extends beyond the cylinder. And then you have a nice intact core of soil that has the same volume as the cylinder core you used to sample it. And it's ready to be packaged up. If you are not sampling more samples than the number of containers you have, you can simply put the container lid on and take it back to the lab. If you have more samples to be taken than the number of containers, you can also just put them in Ziploc bags or other soil sample containers for transport needs. That concludes the overview of the NRCS's protocol for bulk density sampling using a soil core ring. This slide is just to review some of the bulk density concepts we discussed earlier, as well as overview the tips that I mentioned during the protocol description. So remember that bulk density is an important soil health indicator that is a measure of soil compaction as well as pore space. And that pore space in soils is an important area for root growth, water availability and access, as well as soil microbial life. In this image, 2 maize plants are grown in different bulk densities in soil. You can see the limitation of root growth in the higher bulk densities. And finally, a review of some of the sampling tips. Minimize compaction of sampling while driving the ring into the soil profile. Make sure that the internal soil sample is flush with the core sampler ring after you are done cleaning up everything. Remove any soil sticking outside of the core ring before preparing sample for transport. Prevent soil loss while sampling.